plasma, the fusion, VT reaction, everything. I hope it's not overdose. You all are ready to hear about So you must have understood that generating plasma, getting the energy to heat it and to refine it, it's not that simple. It's a bit complicated. But good things take time. So go through these complications to harness the energy. And that is what exactly happens too. As the name indicates, it's a experimental reactor. The first thing, is it first kind of fusion reactor or do we have other fusion reactors also? You know that? Do we have other fusion reactors also? We have. The best fusion reactor before ITER is the JET. I think they must have this, yes. Joint European Programming was built by European Union. But how ITER is different from the other tokamaks, other reactors? JET is also working successfully. But the major difference is in any of the reactor, in any of the tokamak, till now, the the output power is not more than the input, what we give. That means we are not gaining the power in any of the tokamak, any of the reactors. This is the first kind of reactor in which we gain power. The output will be more than the input, and that will be 10 times more than the input power. This tokamak for this reactor is not for the commercial use. It is just to assess whether we can do it. We can get the output 10 times more than the input. That is why it is the experimental reactor. So, all the physics and principles you have heard about. Now we talk about a bit of engineering challenges because as sir has already talked that there is a much temperature difference. You have the temperature at 4 degree Kelvin up to the millions of degree centigrade in the same machine. So it's not easy to use the existing materials and to build the machine, to build the engineering. So we had to go through many challenges to fabricate, to manufacture this kind of machine, basically the Indian part. So we'll talk about that. No, I'll have to this one. No, thank you. It's not connected. Okay, yes, sir. No. Yes. Okay, fine. I think should skip that's very basic. They all have that idea. Yes. So, with the reactor, you know that it's a big machine. There's a number of components, right? Lakhs of components. So, how the engineering and manufacturing of those components is very important. How we design the component, how we manufacture the component, how we test that. The first thing, how we the engineering of component. What comes in the picture is the engineering. The first thing is when we visualize, when we are going to manufacture the component, the first thing is how it looks like. What will be the size? Does it follow the quality standards that we have set? When we find that, the next thing is where it is going to be used in the machine. There must be interfaces, there must be other components also, so there must be other loads also. Those components will offer the nearby component. So we have to assess what kind of loads will be offered to that component which we are going to design. After that, now we have assessed the loads. Now we have to see how this component will react to those loads. These kind of calculations we will do. After that, the codes and the standards what we have set, according to those, the designing and the physics calculations will be done. And then there is a very important part is tolerances. Suppose I've designed something, I've designed a component, and I have to manufacture it. It is not necessary that my final product will be exactly same to the design. All the dimensions, the shape, and the size It may vary because the manufacturer can find some difficulty in manufacturing that component exactly what I have told him. So, but he makes some deviation, he makes some difference, but the component will work well. It does not affect the functionality. So that much change we can accommodate. That change is tolerance. This much change I can tolerate with the functionality. So those kind of tolerances we have to define before starting off manufacturing. And when everything is said and done, designers please know how component is going to be manufactured. Now what manufacturing takes with component. First thing is material. With such adverse conditions, 14.1 mega electron volt neutron, such high melting power, such high temperature and such low temperature, we cannot use the normal materials to face this kind of reaction. So first we have to see what kind of materials we need. Then we have to check do we have these materials or we have to develop. When this is done, after that, in the last slide you have seen the design is piece, how the design is piece. Now we have the material. Then we have to go for manufacturing. Then we have to decide what does it take to manufacture the component of a design of a particular material according to the design. There may be some resources which are required. Suppose I have a stainless steel. I have a particular structure that I have to make from that steel. Right? Design is there, material is there. Then I have to go for what kind of machine I need to manufacture that component. There will be cutting machine, there will be CNC machine, there will be welding requirement. So all the machining requirements we have to assess. After that, we have to see what quality requirements we have to follow. There is a very important thing about ITER. Although the Indian part we are manufacturing in India, Indian manufacturers are doing that. But finally, the system is going to be integrated in France. So we have to follow the very stringent quality rules and the safety rules and regulations of France. It's not the Indian safety rules and regulation. So that part is very important. So we have to check all the quality assurance and the requirements that have to be followed for that company. Then we have design, we have material, we have our quality criteria, we have the resources which we need. Now we have to identify the industries, which are because not every industry can make. We have to identify that which industry can make my design into the actual product. So we have to identify the industries. Then we have to go for the prototype. Have you heard this word prototype? Yes. What is this? I know it. I know. Prototype is I so prototype. An example of the original. Yes. Yes. Right. So why do we do that? To find any faults. So that we don't make any mistakes in the final. Yes. Exactly same. Here we are doing it either. You know the big components and all the machinery is very expensive. It takes time to manufacture. We cannot wrong in the actual product manufacturing. So first we'll make the prototype, and there are two types in prototype also. We can go for the scaling. We can make the small prototype. We can impose all the quality conditions, all the safety conditions, all the codes and standards, everything on that prototype. And if it is successfully manufactured, we can go for the actual product. Sometimes we go for the one-on-one, the actual size prototype. Right? It depends that how it will work in the actual size. If your smaller one, smaller parameters can actually work for the actual one, then we can go for the smaller prototype. But prototype is very important because we cannot go wrong for the actual prototype. Right? When we get the confidence while making the prototype, we get the actual prototype. Yeah, when prototype is successfully completed, we can go for the manufacturing of actual product. This, yeah. So whatever India has done and India is doing, what are the branches in which we are working to make possible. Different kind of materials, heavy and precision engineering, joining of materials, multi-ampere megawatt beam technologies, RF technologies, electrical engineering, cryogenics, hydraulic, diagnostics, prototype that we just have discussed. Stringent quality requirements are that also we have discussed. Documentation, huge documentation is involved, and performance and testing. So we take this one by one. Yeah, before going to the actual manufacturing or actual practice, first thing I have already talked about that we have to follow the French rules and regulations for safety. That's very important. Another thing is for the quality requirement. See, ITER is going to continue for a while. It's a long time process. And many of the components are not maintainable or maintainable within limit. So, quality norms, quality standards have to be followed very stringently. So, these things we have to keep in mind while designing any component, while manufacturing or testing any component. First thing, as we discussed, there are such vigorous conditions. So, materials. What kind of materials we can use? Such a huge temperature, such a low temperature, high heat flux. So, we have to check whether we have the materials. Many materials have been developed for this particular project in India and the outside India as well. We have taken some examples. Chrysler, that you have seen the first one, the leftmost. You have seen in the last slide, Chrysler. It acts like a. What did you understand from the Chrysler? What it is in Eden? Sorry. Actually, it works as a vacuum type of thing for Eden. Plasma is generated. There will be a vessel in which plasma will be generated. There will be magnetic field coils and everything. Like this is the basic thing you understand. But it has to be separated from the environment, right? That is why this is so huge. 30 meter by 30 meter. You can imagine that building. This separates the machine from environment. Now 30 meter by 30 meter. It's huge. Manufacturing is a different thing, but in material also. Then there's one more thing. In the material also, there is a the term is radioactive inventory. We have to be very careful while developing the material that there should not be any component or when react with the high energy neutrons, there should not be generated any component which is any element which is radioactive. So that has to be taken care of. So in this material, this is made of stainless steel. The grade is 304, SS304. Are you guys aware about these stainless steel grades, different grades? Okay. Stainless steel is proper, right? What is the property of stainless steel? Why we use generally stainless steel? Sorry? Strength. Yes, strength. Yes, it is not prone to corrosion. It is highly corrosion resistant material. It has high strength. So, in most of the cases, we are using stainless steel. Particularly, we are using this grade SS304 for the price tag. It has very high strength and very corrosion resistant compared to other grades. And L. 304, 30L. L stands for low carbon. Low carbon grade. There is one interesting thing that if you see cobalt percentage, cobalt you all are aware about? Cobalt percentage is less than 0.1. Whatever steel is available in market, it will be available. Steel is not a problem. This is 304. It's very well available in market, but the cobalt content is not that good. It's 0.1. So it had to be protected. Why we need the cobalt content very when neutrons emerge out of plasma, there is a possibility The neutron may react with cobalt and then cobalt may become radioactive. Right? So we have to keep that cobalt very, very low. So especially this steel has been developed to make Chrysler. It has been developed by Jindal Indian Steel. You must have heard of it. Sorry? That I am not aware, but they have a plant in Odisha. There it has been. Second example here, uh, is the bolted steel. Last we have heard about the bolted steel. Boron, periodic table. What is the atomic number? So while we are using this bolted steel, where we do need that? Electrons are emerging from the plasma. Energy of, sorry, neutrons. We are using the energy of those neutrons. We are harnessing that energy actually for electron. But there is a vacuum vessel which is containing the plasma. Vacuum vessel has double wall. It's not a single wall vacuum vessel. There is a space between two walls. Now, what happens if all the neutrons have not been harnessed, have not been used for heat, for energy, and there are some stray neutrons that cross the boundary of vacuum vessel? What will happen? After that, superconducting coils are there. You go to the superconducting coil, heat will not be destroyed, right? So you have to put something in between that can stop the neutron, right? Now, what we can use to stop the neutron? We have to find such a material which has this ability to stop, to suck the neutron, which must have the higher neutron capture cross section. Otherwise, you can use any material. Neutrons will just penetrate and go to the top, right? So we have to use that special material which can capture the neutron. Boron is such material which has higher neutron capture cross section. So we what we did, we just added a little boron in stainless steel. Its composition was different. We added boron, but it's not that simple. Boron element has a property, it is brittle. So when we add in the steel, the brittle boron, and when we form that steel, when we fabricate that steel, it is difficult to fabricate, it is brittle. It forms cracks in that steel. And the maximum percentage boron which we are using is 2.25% boron. So it was a huge task to make it possible that we form this stainless steel with boron. But actually it was done, and now we are using this bulleted steel to manufacture the blocks, stainless steel blocks, which will be put between the double wall of vacuum vessel just to stop the neutron so that our magnets are fine. Third example we have taken copper, chromium, zircon. You know, when you have the high heat flux, very high heat, material, any material you are using, the conducting material or any material, at such high temperature, it may lose its properties, its strength, hardness, anything. It may not behave exactly the same what it behaves at room temperature, right? So we had made this alloy, copper, chromium, and zirconium. It can stand up to 10 megawatt per meter square. This much heat flux it can sustain and it can transfer that easily. So this was also developed in India, this material, especially for heat. So these were the few of the challenges we face in material manufacturing. Now we come to the actual manufacturing, the outer part, the vacuum type container price we have talked about. 13 by 13. Can you manufacture in one go? Single component? Is it possible? It's very difficult. 13 by 13. And manufacture and to deliver. See, just imagine how difficult it would be to transport from India to France because ultimately it has to go to France. So what we did, we adopted segmented approach. He just made it parts. It has been made in four parts. Then the single part has been again made in sub parts, right? So this 35, see, it has a weight of approximately 56 Boeing planes together, 2,300 ton of weight. So it's that heavy. And it's not just the weight you have to handle, it's all about the precision also. When you manufacture it, you have to manufacture it precisely. Tolerances are very stringent, so you have to follow the tolerances also. And the other thing which comes in picture, when you manufacture this, when you manufacture the small parts of cryostat and you join together, how will you join them? You have to stainless steel parts, how will you join them? Welding, welding you have heard about? The different kind of weldings, welding techniques which have been developed for this project and which have been adapted. So then welding comes in. You join the different parts. Now welding also is very challenging because it's not necessary that you are joining similar kind of material or similar kind of thickness. Suppose you if you have 10 plate and 10 and you fuse together, you join them in the welding, it's simple. But you have a plate of 105 thickness, another is of 200 thickness, and that you have to weld. And you have the distortion limits. It's not that you can weld by any method. There are limit of distortion, that this much distortion is only allowed. So that was again a challenge. So different welding techniques have been developed, and different validations have taken place that this particular this welding has been done properly. Different quality checks were there. So this is the example of charisma, the bottom part. See the segment in the first picture. There is a segment, and there are number of segments such type, and together it forms the base for price. Yes, this is the right one. This is charisma what we have already delivered the part to France. Okay? And this is an Indian building there at this side of the. In this building, all the components which are there have been delivered by India. All the components and the people who are working there for the welding and everything, they all are supervised by Indian engineers. So it's called Indian home welding. Yes, this is another example of heavy engineering. This is the lesson for the experiment we have made in our. This is there in our laboratory. It's 10 in the height and 4.5 meter. However, meter is the diameter. So you can imagine this meter, almost 5. That is the size of this vessel which has been made in India. Now, along with the heavy engineering, then now we have discussed that how much steel we have dealt with, how much is the size, how much is the weight. It's not the only important thing of weight, heavy engineering. It has to be precise also. Let us take the example of precision. You have a light source and you want to get the image at the plane, the third one. And in between, you have a slit of a particular size. Right? Like through this slit, you form an image. It's very simple. When you want a larger image, just slit will be little large. You get the larger image. But difficulty arises when you have more than one thing in between. If you want to have the optimum image, these slits, these apertures have to be aligned, right? If these are not aligned, what will happen? You will not get the optimum size of image. Just imagine that there are 3 planes, right? Maximum in this picture. And in each plane, there is one aperture. Just imagine if there are more than one aperture in a plane and there are 3 planes. So, how difficult it would be to align them. Exactly what we are doing. precision we're using in the, there are three planes. I can also that. These are the three planes, right? And these have total 1,280 apertures. And all these apertures have to be aligned. So prominences, the flatness, the linearity, angular displacement, it has to be very, very straight. You can see the positional accuracy, the flatness of the plane, the angular accuracy is very, very small. These have to be aligned properly. This you can see. Structures. We discussed about the flatness, right? In the previous one. What is rising? Rising. Even no problems. Yes, yes. You raise your hand. Okay. What is that? We discussed about the relation temperature we are dealing with. Very low to very high. So the very low temperature is for the cryo. So the substance which needs such low temperature are called cryogens. And the branch which deals with it is called cryogens. Right? So here we are using such low temperatures. Why we are using such low temperatures? Why we are dealing with because it's difficult to create such temperature. Why we need that? We discussed about superconducting points, superconducting magnets, right? Superconductivity, does it have any relation with temperature? How conductivity varies with the temperature? How resistance varies with the temperature? Resistance also decreases, right? The conductivity increases. Fine. And what is superconductivity? That you have that we have already told. Resistance becomes almost zero. So it tends towards zero. So when you need that resistance tends towards zero, you need a low temperature for that, right? When temperature just slows down, resistance also slows down. That is the relation between the temperature and resistance. So when you need the superconducting magnets, you need a very low temperature to maintain that superconductivity. Not at room temperature you cannot maintain. That is where right comes in. Temperatures we are using are 4 Kelvin and 80 Kelvin. How these superconducting magnets are made? These are small and very thin strands. These are mixed with copper and stay in stainless steel jackets. They are put together and they are cryolized to fetch this cryogenic temperature wherever it is required. And you know the length of these superconducting strands total which is used in this is 1 such. This the magnets. Here if you see, there are two kind of field coils. You what about the plasma confinement? How it is confined? Magnetic field. Any charged particle, if you want to confine it, you need a magnetic field for that. So there are magnetic field coils in both the direction, vertical as well as horizontal, to trap the this plasma and to create the fusion. So these are the magnets. Although India is not manufacturing the magnets, but India is going to provide the cryolites, which carries that low temperature to the magnet. So that is what it is. Cryolite. You have a cool rock, which core temperature is rising temperature 4 degree Kelvin or 80 degree Kelvin or whatever you want. And that temperature you have to that has to be reached to the component wherever it is required. So you need the lines, the stainless steel lines are there, the pipes are there. These are called cryolines, which TD is going to deliver. Now, what is the difference from the existing cryolines in this figure? These cryolines are being manufactured in India, in Baroda, and for two Indian industries they are making. What is the special thing about this cryoline which is not there in the other components? In one cryoline, there are maximum 7 pipes, 7 lines are there in one cryoline. So next here, you can see that this one, in a single line, there are different pipes. So you can fetch the cryogen of different temperature in a single line because there are 7 pipes, there maximum 7. This is the specialty of Cryolines, which is being manufactured in Baroda.
Cryolines are not simple pipes. Remember that very complex structures. So you're carrying liquid nitrogen, liquid helium, which should not be exposed to air. So the whole tube is in vacuum. It's very complex. It's not just simply pipes. Remember that. Okay.
This is another one. There are two prototypes are being manufactured. This is another one in the lab design. So why we went for the two prototypes? We discussed about the importance of prototypes. Sometimes we go for one prototype only, and sometimes we go for. In this case, we went for two prototypes. What are the benefits for two prototypes? What can be? Yes, yes, less risk. When you have two options, probably more sure. You can do whichever is better, you can go for that for the ITER manufacturing. And there is one more thing. When we go for the demonstration reactor, the Indian reactor, we have two industries which are able to face the challenges. So at the same time, we are developing two Indian industries. So that is also very big reason for it. So these are some pictures of cryo facility at ITER in France. You can see here that cryo have been installed there at site. Now the next challenge was the cooling of the system. Cryogenics is used for the temperature which is less than zero. You know that in Kelvins, right? But depending on the distance where it is in the machine, you have to use the different temperatures for cooling. It is not necessary that every time you need 4 degree Kelvin or 80 degree Kelvin, right? Heat will be generated in the tokamak in heater, so that heat has to be rejected. You cannot, if your machine will be heated every time, some point of time it will stop functioning. That has to be cooled down. There is cooling system which is called cooling water system. It has different problems, different cooling water system, primary cooling system, secondary cooling system, tertiary cooling system, depending on where we are using. Suppose we have components which are directly facing to plasma. Cooling will be different from the components which are far away from the plasma, right? So based on that, there are different kinds of cooling systems. What India is going to manufacture is secondary cooling system and tertiary cooling system. So this chiller is specially made for the cooling system. It has power is 450 kilowatt. This is first time such powerful chillers are made in India in Pune. There are 6 such chillers have been made. And no, it's fine. In very first talk, we have heard that we heat the plasma. Then only fusion can take place. Right? Plasma heating we have heard. So these are the different heating systems that we are going to provide here. part of it that will be used to heat the plasma. It's different heating systems. Now, heating is also a very interesting thing in heater. When you have different in plasma, you have ions, electrons, neutrons that you have to heat, right? So, will you give the same kind of heat to every particle? See, have you heard of resonance? When frequency resonates, there's a maximum heat transfer. You know, the electron and the ion, positive ion, they have mass difference. Electron is very, very light. So it is just rotating. It's called gyration, but I will not go into that. It's rotating. Ion is also rotating. So according to their mass, this will be different, right? Suppose you have two students in class. One is very bright, other one is not. Kind of coaching or kind of attention teacher gives, it's different, right? So exactly with the electrons and ions. They are rotating with the different frequencies. They have different masses. So to transfer the maximum heat, there are different heating systems for electron, for ions, for neutron. So that is also very interesting that you for each and every particle you have different kind of heating system. These are some examples of heating system. Like, see, this power supply has been made by India and it is working in Italy, Padova. In that system it has been used. Another example of ion cyclotron radio frequency heating system. It's used for ions in plasma. This is for the electron cyclotron resonance plasma heating system. See the frequency which is being used 170 gigahertz and compare it with the frequency what you're using in your microwave. It's only 2.4 gigahertz. So this much high frequency. There is no instrument, there is no heating device for the heating of electrons with such high frequency till now. It's especially going to be manufactured for ITER. And there will be 24 such devices in India, and out of those 24, India is providing two facilities, two supplies. Quality requirements also we have discussed that international quality norms. So, taking the part of ITER, manufacturing fusions in ITER, has a benefit that when we manufacture components which are going to be integrated in France, we are developing the Indian industries according to the international quality standards, according to the international safety standards. That is one benefit. That now Indian industries are being equipped with those kind of facilities. Second requirement, apart from the technical and the manufacturing and scientific, the documentation requirement in ITER is very huge. As you've seen the machine, the picture of the machine, of course, machine has not been made yet. It has lakhs of components. And every component, when you design, there is a process of material selection. There is a process of finalizing the design. There is a process of testing. There are number of iterations, number of failures also. Then again changes in the design. And we have lakhs of components in Eagle. So all these things, all the changes, all the records have to be documented properly because in any of the operation, if anything goes wrong, it can backtrack, it find out with which component actually things went wrong. So proper documentation is very much required for this and we are following all these.
How much time required more? Because they are hungry now. It's already
I'm
1:30
so
class.
sorry, yeah, I can't. It's 1:45. I'll take this 5 minutes. Okay. So we have a laboratory in Gandhinagar, India laboratory, and the aim to set up this laboratory is to provide all kind of facilities which is required to develop all the deliverables which we have to deliver to France. These are different sections I have told you that the cryo lab is there, radio frequency lab is there, in which the power supplies and everything is being used. Diagnostics lab is there. Diagnostics is another very interesting part of it. Is when plasma will be generated, one has to check what are the properties are there, because you cannot simply sit and say that okay, plasma is generated, this much will be the temperature, these are the properties. So there are things, there are the instruments, there are the machines which will be used to diagnose the property of plasma. So there is another branch, diagnostics lab is there, then beam development lab is there. This is one example. And this whole structure, this is beam development. This whole structure will be put in that vessel which I have shown in the previous slide, a 10-meter long vessel. These are the different industries which are involved. These are directly involved in the part which India is making, and indirectly, because these are also some subcontractors. So indirectly, hundreds of industries are there which are involved in this project. Indian industries. So I summarize the main, the most beneficial thing in ITER is that although we are contributing 9% as part of ITER, but what we are getting in return is 100% technology. So that is the main benefit of ITER. And we are getting, our industries are getting equipped with all the quality standards, the equipments, and the safety norms according to the international requirements. These are the main benefits, and of course, the norms has been learned, and still we are in the learning phase. And I hope that after a few years, we will be ready to make to fabricate our own reactor after ITER, after successful completion of ITER. Thank you.
Thank
Questions
you.
are like want to ask something?
No.
Yeah, and please. How can the transport that machine to the transport? Okay. Yes,
Sheep.
that is the reason that there are seven. In the previous talk, you heard that there are seven partners. They are making few parts. All the parts which are being used in tokamak, they will be manufactured by different partners, right? And the machine will be fabricated in France, but then it will not be transported to somewhere. It will be fabricated. It will be situated there only. And when other partners have to use it, they'll have to manufacture based on that design. They'll have to manufacture their own device, their own tokamak. So it is not going to transport it anywhere.
If you come, I can give some